see, I don't see my slides yet.
Okay, I think it's showing your screen now.
Well, I still don't have it. What we may have to do, Dora, is do it from the hard copy, unless you could give me some instructions. It says connected to GoToWebinar.
Yeah, if you minimize that window at your top left hand, just go ahead and minimize that. Oh, I think that's going to make you leave it. Did it take you off?
Well, we're having some issues. So if you don't mind, I'm going to go ahead and just ask you to promote or to
Sure.
advance the slides.
I'll be glad to do that.
All right. Well, welcome to our webinar. I'm gratified that the interest in application of CSI to monitored natural attenuation has taken off like it has. I think it has great potential to be a powerful tool. It's starting to reveal itself as an important alternative line of evidence in support of M&A remedies and in design and performance monitoring for active cleanups. So if we could go to the next slide, slide 1. Many of our sites are what I call bullseye sites, where there's no general consistent direction of groundwater flow. And so the plumes that form are irregular and are almost stochastic. So you have a highly concentrated center of contamination surrounded by roughly a periphery of gradually diminishing concentrations in any direction. These plumes are hard to monitor, and they're hard to interpret. Next slide. I was asked to evaluate a 5-year record of decision review for this particular site, which is in Louisiana. And so I worked it up in terms of where the concentrations were and what the trends were in concentration. And so basically this just shows the frequency distribution of the total chlorinated hydrocarbons in monitoring wells at the site, comparing the highest concentration that was ever sampled at the site to that concentration at the time of the review. And you can see that over the entire site, the concentrations of contaminants have decreased significantly. So overall, monitored natural attenuation is an ongoing and valid process. Next slide. However, if you look at individual wells, what you'll see is many of the wells that have the highest concentrations show an increasing trend in concentration. And this is the sort of thing that gives regulators heartburn as well as responsible parties. And so the question is, are these increasing trends significant, and do they require some modification of the record of decision? Do we need to do something different at this site to properly manage the contamination? Next slide. So we're going to look in some detail at what's going on in this most contaminated well, well number 23, where the concentrations appear to be increasing. Next slide. So we can see for well 23 that by the time they put in the monitoring system, TCE was already essentially gone. Concentrations of cis-DCE and vinyl chloride increased over time initially, then concentrations of cis-DCE declined while concentrations of vinyl chloride continue to increase. And then in the last 5 years or so, it may look like the vinyl chloride concentrations are going down. If you show a figure like this to a regulator in the United States and ask them, well, says, I believe that vinyl chloride is degrading at this site, you'll get a look of skepticism and bemusement, like, okay, I don't see that in the data. So what we're going to try to do as use CSI approaches to take another way of looking at the behavior of the cis-DCE and the vinyl chloride. Over on the right-hand side, I gave you the actual concentrations of vinyl chloride so that you can see that these concentrations are actually quite high and are of some concern to the regulatory authorities. Next slide. Compound-specific isotope analysis relies on the fact that most elements in nature come in different flavors. Stable isotopes that have, of course, the same number of protons and electrons, but different number of neutrons, which means that the mass of each isotope is different. For example, the two abundant isotopes of carbon are carbon-12 and carbon-13. And the heavier isotope is roughly 1% of all the carbonates on the Earth. There are also stable isotopes that can be used for chlorine and for hydrogen. Next slide. So there is a device available that actually measures the ratio of the isotopes, and it's called a stable isotope ratio mass spectrometer. And what it does is it actually compares the ratio of heavy isotope, its abundance, to the abundance of the more common isotope. And so it doesn't give you a concentration. The instrument actually reports the ratio of the two isotopes. Next slide. If you're not familiar with the geochemist, because the instrument was giving us a ratio, decided basically to work with that and make that the data format for reporting isotope analyses. And so the symbol for the ratio of carbon-13 to carbon-12 is expressed as a change in the abundance of that against a standard. And so that's read as delta 13C. Since those changes are small numbers, they're usually multiplied by 1,000. And so that's delta 13C per mil. So when you send a sample off for compound-specific isotope analysis, your results will come back with this format. I just give this to people that are not used to it or have not seen this particular convention before. Delta 13C per mil. Next slide. That's the definition of what it is, basically. It's the ratio in your sample divided by the ratio in an arbitrary standard, but it's a fixed standard used internationally. That ratio minus 1, and then multiplied by 1,000. So that's what delta 13C per mil would be. Next slide. Now let's see how this delta 13C per mil changes during anaerobic biodegradation of chlorinated solvents from TCE to cis-DCE to vinyl chloride to ethene. On the left side, what you have is the concentration of these particular compounds over time in a microcosm study. TCE disappears to be replaced with cis, cis disappears to be replaced with vinyl chloride disappears to be replaced with ethene. On the right-hand side, you have the delta 13C per mil of those four compounds. And you'll see as they degrade, basically it moves up in the figure. The value for delta 13C becomes less negative. It becomes heavier, which is to say that it has more of a higher isotope in the sample. There's a dotted red line in the right-hand side of the figure. That is the beginning value for delta 13C in the TCE that was originally dechlorinated. And if you compare the left figure and the right, you can see that when the parent is pretty well depleted, then the daughter will rise above that dotted red line. And so as the value for delta 13C per mil becomes less negative, heavier than the initial condition of the parent, then that's evidence that we've got degradation of the degradation of the daughter product, further degradation of the daughter product. Next slide. This is just another microcosm study that has a little better detail on what's happening with the TCE. Again, you see as TCE disappears, its concentration goes down. The delta 13C for TCE gradually increases. Go to the next slide. The relationship between the change in concentration and the change in the value of delta 13C is called isotopic enrichment, and it's described by a coefficient called the isotopic enrichment factor. This is a simplification. It's a little bit more complex than this, but most of the time, basically the uncertainty in some of the data don't justify a model that's any more complex than this very simple model. So the actual delta 13C of the TCE or whatever you have in the groundwater is equal to its original value before it started to fractionate during biodegradation, plus epsilon, which is the enrichment factor, multiplied by the natural log of the change in concentration, the normalized change in concentration. Next slide. So we're going to take this data for TCE and try to extract a isotopic enrichment factor. So you have concentrations of TCE going down over time. You have delta 13C per mil increasing over time. Next slide. This is the simplest way to do it for me, at least. You simply have the concentrations over time, and so you divide the concentration at any time by the highest concentration. That gives you the fraction remaining, or C over C naught. You take the natural log of the fraction remaining, and now we're going to plot delta 13C as a function of the natural log of the fraction remaining. And that's in the next slide. And if it fits what's called the Rayleigh model, you'll get something that's fairly close to a straight line. And the slope of that straight line is the enrichment factor, epsilon. So in this particular case, it's minus 14.7 per mil. So you'll find tabulated values for the enrichment factor, and I just wanted to show you where they came from and one way of extracting those numbers from the primary data. Next slide. So how do we use measured values for delta 13C? This is what's reported by the analyst when you send your samples off. And enrichment factors, which you usually get from the literature, to put a boundary on or an estimate on the extent of degradation that's occurred in the groundwater that you sampled and sent off for analysis. So we're going to work through a hypothetical situation. Imagine that we were doing in situ anaerobic bioremediation. We submitted a water sample for compound-specific isotope analysis of TCE and returned a value of delta 13C is minus 10 per mil. So with that number, how much of the original concentration of TCE was removed? Next slide. So I gave you that. I took that formula that I gave you for the Rayleigh equation, I just simply rearranged it. We're going to try to solve this knowing the fraction remaining. We're going to try to solve for fraction remaining, rather, knowing the values for delta 13C and the value for epsilon, the enrichment factor. So what we're trying to get is F or C over C naught, knowing the delta 13C values and epsilon. Next slide. There isn't a, I wish it were exhaustive because it's not, but and it's fairly dated, but there is a fairly lengthy list of values of epsilon available in the EPA guide. Almost everything that I'm going to talk about today is simply excerpted from this EPA publication, and it's available at no cost on the web. And so if you really have interest in this subject, this is something that I would direct your attention to. I think you'll find it useful and valuable. And in the very back of it, it's got a list of fractionation factors. Next slide. So it's listed by compound. and it gives the value of epsilon, and it talks about the conditions and of the bacteria that if they know what was responsible, and then the primary literature citation if you want more details on that particular experiment. So we can see for TCE that under anaerobic conditions, you can get quite a variety of values for epsilon. Somewhere around -20, in the top, somewhere in the middle, it's from -6 to -2. The one in the bottom kind of splits the difference. It's -7. Moves around quite a bit. Next slide. So let's see what that does in terms of predicted values of the fraction remaining. So I've simply taken the equation, and I'm going to insert my -10 value for the delta 13C measured in groundwater. I'm going to assume a value of -24, which I'll justify to you shortly, for the original concentration, and then I'm going to divide it by the value for epsilon that has the lowest absolute value, the one that said -2.5, and see what that says. And so simplifying, then it's going to be e to the -5.6. I know as large as the group is, there's at least one person out there that doesn't know how to solve that equation. So for that one person, if you go into a spreadsheet such as Excel, enter the equation equal to exp parenthesis -5.6, and then press check, it'll solve it, and it turns out that C over C naught is 0.0037. In other words, more than 99% of it is gone, that particular value of epsilon. Next slide. So what I've done in this figure, starting at -24, is I plotted the fraction remaining for different values of epsilon. And what you'll see is that when epsilon has a small absolute value, you get a lot of degradation for a small change in the delta 13C. When epsilon has a large value, you get a smaller change in degradation, a less extensive degradation for the same change in delta 13C. So a value of -10 would correspond to 0.0037 for the line that's -25 per mil epsilon. And if you looked at the one for -7 per mil, well, it's not even 90% removal. And if you look at the line that's -22.9 per mil, well, let's see, it looks like that's that's about 60% remaining. So it's very sensitive to this value of epsilon. And if we only were able to make projections with this kind of data, actually, I think we'd have to say that there would be little value added. Let's go to the next slide. So if we're looking at just TCE and we're looking at reductive dechlorination, it's really not all that helpful to us because of the very different values of epsilon. This is related to the fact that there are a lot of different kinds of bacteria that can degrade TCE to cis DCE using different mechanisms and producing different fractionations. Next slide. But that's really not what we're trying to do. I mean, we know TCE is degrading because we have cis and vinyl chloride accumulating. So we really don't need the CSI to prove that. What we're really interested in is whether these daughter products are degrading. And so let's go to that question. Next slide. If you have a situation along the flow path where the parent is pretty much entirely degraded, my operational definition of that is 95 to 99%, you can assume that the original unfractionated delta 13C for the degradation product was the original unfractionated delta 13C for the parent. What this assumes is that all the carbon that was originally in the TCE got turned into carbon that was in the cis. Next slide. This is a hypothetical plot of the basic operating paradigm for how fractionation works. The red line is fractions remaining of TCE plotted against delta 13C, so you see that it starts at some value, in this case minus 30 per mil. And as the TCE degrades, then it becomes heavier. The dotted red line is that original value. The dotted blue line is the instantaneous delta 13C of the cis that's produced from the TCE at that moment. And you'll notice that the separation of the two lines is constant. That constant is the value for epsilon, the fractionation factor. But that instantaneously produced cis is added to cis that's already present. So the solid blue line is what you actually measure, all of the cis that's in the sample. And you'll see that it initially starts at a value, in this particular case about minus 17, below the value for TCE. And then as the TCE is pretty much entirely consumed, it approaches the initial value for TCE at the beginning of the experiment. So this is the model that we're going to use to try to understand the behavior of cis. It has some assumptions. The most important one is that all of the TCE gets turned into cis. Next slide. I think most of the time that's a fair assumption, but we do have a paper, I'm a minor author on this paper, that's in the process of review. I hope it'll be out shortly. But Pat McLaughlin with Microseeps has come up with a way of figuring out what the contribution might be if you had an alternative pathway that was stealing some of the TCE so that it never showed up as cis. And what Pat has done for the particular data set that I'm showing you at the particular site is he's made some assumptions, each one a boundary limiting assumption on abiotic transformation of TCE to other products, and then seeing what that would do to the final degradation value for cis if there were no degradation of cis, the final delta 13C for cis if there were no degradation. And that comes out to minus 14 per mil. Now that is specific to this site and the conditions at this site. And it's one of these cases where you multiply the worst case by the worst case by the worst case by the worst case. And the calculation, the absolute worst case in the literature is considered. And so it's an absolute boundary. It can't get any worse than that, in the sense that the true value has to be something more negative than minus 14. But it's a reasonable boundary. And we're going to use that to separate what might happen from what there's really no doubt can happen. Next slide. So now, how can we all use all of this? And I've spent a good part of my time talking about theory. How can we use it to actually determine what's going on in a real site? Next slide. We have to know what concentration of TCE we started with. The problem with that is we almost never know. I'm sorry, the delta 13C, the isotopic fractions in the TCE that we started with. We almost never know that. But we do have some reports in the literature that give us a range. Next slide. And those reports in the literature have been upgraded, updated a little bit. This is the latest information I've seen on the range of delta 13C for TCE and commerce. Next slide. So what we're going to do is assume that our starting condition was at or more negative than the least negative value for delta 13C for TCE and commerce. I'm going to use a value of minus 23 per mil. So that's what that blue and that red thing identifies a space where we would expect it to start. In other words, that'd be the original concentration before it fractionated. Now the two sloped lines are basically the change that you would expect based on two values for epsilon. Next slide. I went through the literature and looked at the reported values for delta 13C of cis DCE during biological reductive dechlorination. And the values range from minus 29.7 to minus 14.1. Next slide. And so we're going to assume that the least fractionating would start at the highest concentration, and the most fractionating would start at the highest delta 13C. The most fractionating would start at the least negative value for delta 13C, and that defines a space where degradation would control the value of delta 13C compared to C over C naught. So that's the red space. And then the blue space, dilution or dispersion should not significantly fractionate the TCE or the cyst. And so the blue space is C over C naught that's caused by dilution or dispersion. Next slide. All right, so here's some fractionation factors for vinyl chloride. Next slide. And so here's a plot for vinyl chloride that compares values for epsilon, highest and the lowest in the literature, and to define a space where degradation would control delta 13C against C over C naught, and then the blue space again, where there's no fractionation and it's just simply caused by dilution and dispersion. Next slide. So let's go back to well 23. Finally we're going to get to the point where we're actually going to start to do something. Next slide. I showed you this before. The question is what's happening to the cyst and what's happening to the vinyl chloride. Remember, these plumes are bullseye plumes and the water flow is erratic, and we really can't tell if the concentration is going down because stuff is being degraded or if simply the water in the plume is moving away from the well. So we're going to try to distinguish between degraded and move away. Next slide. To define C over C naught, I simply took the molar concentrations at the time the compound isotope analyses were collected and divided those by the highest concentration encountered at any time in the monitoring record. Now, it's a bounding value, but that's the best that we have from the data available. So C over C naught is what we are right now divided by the worst it ever was. Next slide. So for this particular well, this is where cis DCE plots. We get a pretty heavy number. It's a little bit above 0. And so there's no doubt that cis is degrading, not simply diluting, or that the water moved the plume away from the well. Next slide. Now, vinyl chloride was the one that was problematic. If we didn't have a significant alternative degradation product, if that did not happen and all of the TCE turned into cis and all the cis turned into vinyl chloride, then it's above that range of dilution, and we can say that vinyl chloride behaves as if there's a combination of degradation and dilution. Can we go back a slide to slide 38, Dora? You'll notice if you go along that x-axis, the distance is sort of equivalent to a factor of degradation. And so if you go from 1 to the middle of the degradation area, and then from that to where it is, about as much of that removal is dilution as is degradation. So what's happening with cis is a combination of the two, and they have roughly equal importance. Okay, now let's go to 39. You'll notice that vinyl chloride shows the same pattern, maybe not quite as much dilution and dispersion because the degradation space is wider. But it shows that if there is no competing degradation pathway besides biological reductive dechlorination, about half of the removal is caused by dilution, half of it's caused by the bugs. Now, we don't know for absolute sure that it's caused by the bugs because it's below that value where we have the absolute boundary based on the most conservative assumptions. But this is, I think, reasonably strong evidence that the vinyl chloride is also degrading. And so, next slide. With that in mind, I think it's possible to convince a regulator that that is not all dilution and dispersion, and and you can expect it to continue to go down even though the very last concentration very last sample indicated concentrations were increasing. So this is the point of it. It gives you another place to stand and to look at your trend data in the monitoring record. Let's take a look at the next well. Next slide. And again, the concentrations, overall concentration trend is increasing over time. Next slide. These are the data. It's not increasing very fast and very far, but it is increasing. Again, TCE is gone by the time the well was installed and sampled. We're starting to see maybe, I don't know, half, maybe 20% of the cis is gone, and we're picking up a little bit of vinyl chloride. So what's happening with this? Next slide. Well, the cis-DCE stable isotope analysis falls right in the degradation portion of the figure, though it's a little bit below that absolute boundary. But that's a reasonable indication that it's degrading. It's just not absolute proof. Next slide. And you'll see that the vinyl chloride falls way down in that dilution and dispersion part of the graph, so there is no evidence in this data that there's biodegradation of vinyl chloride occurring in the groundwater as sampled. Notice I didn't say that it's not degrading. The CSIA cannot prove a negative. It can't say something's not happening, but it can say there's no evidence that it is happening. So there's no evidence for degradation of vinyl chloride. Next slide. And at a lot of sites, you really don't expect the vinyl chloride degradation to kick off until the cis is gone. So that's not a surprising interpretation of the data set. Next slide. Okay, let's look at this well, where there's evidence of degradation, but it's not statistically significant at 80% confidence. Next slide. So we had a little bit of TCE in this well when it was installed, but it was gone in a year or so. We picked up a great deal more cis-DCE. It looks like it's going down. And vinyl chloride seems to be accumulating over time. So what's happening with this particular system? Next slide. Well, that declining concentration of cis-DCE is caused by biodegradation of the cis-DCE. No doubt about it. That's not just the plume moving away from the monitoring well. Next slide. And we can tell that the vinyl chloride is degrading because its fractionation is so extensive. So next slide. So even though the recent trend of cis is down but ragged, we can tell that it is being degraded. And even though the concentrations of vinyl chloride are increasing, we can tell that it's being degraded. And so that's particularly good news for this particular well. It's headed the right direction for us. Next slide. One other thing that the stable isotope analysis can do is tell you when the rules have changed. So let's take a look at this particular well. Next slide. It was looking good. Cis was going down, and the TCE pretty well disappeared, not much vinyl chloride, and then in the last two sampling points, everything goes back up again. And so is this basically a well sampling a different portion of the plume? Is the behavior changing? What's going on with it? Next slide. Well, it does look like cis-DCE is being degraded, even though the concentrations have gone up to near the maximum. But that's not an unequivocal call. That's probably what it is. Next slide. And we have no evidence from the stable isotope analysis that vinyl chloride is degrading. So next slide. And so what the CSIA has done is alerted us to the fact that this particular well is problematic and it deserves some attention, needs to be watched more carefully, and if this trend increases and concentrations continue to rise, then that might justify, say, spot treatment, some active remediation that's focused on that portion of the plume that's not doing what we want it to do. Final slide. So if you have any questions that come to mind later after you've had a chance to think about this and that you haven't sent to Dora through the webinar system, you're welcome to send me an email. And if you want to use the Excel spreadsheet that I use to make these plots, I call them Cooter plots, I'll be happy to provide that by email. This pattern of plotting delta 13C against C over C naught and then comparing it to fractionation expected from degradation and dilution was taught to me by Thomas Cooter at the University of Oklahoma, and his analysis of a large data set on MTB and TBA. I simply extrapolated his concepts for chlorinated solvents, and that's why I call it Cooter plots. And I invite your application of his approach and this approach to facilitate the interpretation of the compound-specific isotope analysis data that you will be using to try to answer questions that simply cannot be answered from trends and concentrations alone. You don't want to use CSIA unless you've got a question that you can't answer any other way, but maybe a little more than half the time, CSIA can answer those questions in a way that you just simply can't approach with any other characterization technique. So that leaves us a fair amount of time for question and discussion. And let me see if I can find some way to get to the chat, Dora.
Okay, well, here's the first question that we have, Dr. Wilson. It says, what labs analyze for isotopes and what is the general cost?
In North America, we have two labs in the United States, Zymac and Microseeps. They were recently bought up and now they're parented under Pace Analytical. And so basically you can Google Microseeps, or you can Google Zymac, or you can Google Pace and get to what is now a joint commercial venture. And these labs, in my experience, provide sufficient quality assurance data so that you can understand what's being reported to you and the uncertainty associated with it. You can also get these analyses done at the University of Toronto. And the general cost. Remember, I warned you not to do this for the fun of it. To do these analyses, you really need to do two things. You need to do an 8260B analysis of concentration, and then turn around and do the stable isotope analysis. And the two together are roughly running somewhere around $300 to $400 per sample. Now you'll get some efficiency and a reduction in cost if you ask for more than one compound in a particular sample. So if you wanted TCE and cis and vinyl chloride, instead of that costing you $900, it might cost you $450. But it depends on how many samples you have and how many analyses that you run.
Okay. Has this data interpretation been utilized when ethene is included in the analysis?
It could, but ethene is benign. The only reason, yes, I see now why somebody would want to, though. Often the concentrations of ethene are much less than would be expected from the stoichiometric conversion of vinyl chloride. And the reason for this is that ethene is a substrate for anaerobic biodegradation, and it rarely accumulates stoichiometrically. And so if you wanted to explain why your ethene concentrations were lower than would be expected from the stoichiometric conversion of the vinyl chloride, you could use this approach. But you'd have to go through and collect your values for epsilon for ethene and create your own Kuder plot for ethene.
Okay. Is there a plan to update the list of enrichment factors that's shown in the EPA guide?
No, and that's why I gave you, excuse me, that's why I gave you the references. I went through the process of updating it as far as I could a month ago.
Okay, there's another question that says, would analyzing the groundwater samples for ethene, ethane, and chloride also be a valid method for determining if vinyl chloride is degrading?
Depends on the numbers that you get. If the numbers give you a clear, unequivocal pattern that you can interpret to a regulator, yes. If they don't, then you need to talk to somebody about CSIA. But I would do what's described first, and then if that doesn't work, then go the next step.
Okay, and then this one says, thanks for a very interesting presentation. The analysis shown only seems to evaluate anaerobic biodegradation. Can CSIA be used to evaluate aerobic degradation of cis and vinyl chloride?
It can be used for aerobic co-oxidation of TCE. The fractionation factor is about -2 per mil. It has been successfully applied in groundwaters where the oxygen concentrations were 5 milligrams per liter or higher, and the TCE was disappearing. And at least a few sites in the United States, C over C naught along the plume could be explained by the fractionation of the TCE through aerobic co-oxidation. I don't know if anybody's ever successfully applied it for aerobic co-oxidation of cis. You would not expect that because you would not expect cis production in aerobic water. Now, have I answered that question?
I think so.
Okay.
All right, what's the recommended frequency for CSIA sampling and analysis?
Depends on how big your site is and how contentious your relationship with your regulators is. What I recommend people do is they do a relatively small, focused preliminary analysis to see if there's anything that's going to be useful. And if it turns out that you are getting fractionation and that your data might be interpretable, then you go back and you do a more extensive survey. And there is actually guidance in that EPA report. But generally what most people in the United States do is if they do decide to do the one big one, they'll do that once and then see if that wins regulatory approval. And then they do it again if the regulator wants them to because there's some evidence that the system is not behaving as expected, perhaps as revealed in a 5-year review. It's not something that you do as a routine monitoring tool.
Okay, how does absorption on naturally occurring organic material affect the CSIA approach to determine degradation?
Absorption mildly fractionates the TCE. And so if you are looking at a plume that is expanding and you're at the leading edge of the plume while it's growing, it could mislead you into thinking it's degrading. Most of the time, because we quit using TCE in this country 30 years ago, you're looking at plumes that have stabilized as far as sorption goes. And so sorption no longer has an effect on the fractionation, and it doesn't matter. And so if you're in a stable plume, it's not an issue. If you're in an expanding plume, it has a mild issue, and there are papers in the literature that can teach you how to correct for that. But that would only apply to the situation where you have the leading edge of a plume that's growing.
Okay, can you also briefly reiterate how you and Pat came up with the boundary conditions on the DEL for the daughter products? Was it based on the site data?
Okay, it's based on the idea that iron monosulfide, FES, also abiotically degrades TCE to primarily make acetylene, which you don't pick up as a daughter product. cis is a minor degradation product in that pathway. And so what Pat did is he took the maximum amount of sulfate that was in this site in wells that were not impacted, and he compared that to the sulfate in the impacted wells to determine the sulfate that was consumed by sulfate reduction, and assumed that that sulfate was turned into iron monosulfide. Now, we don't know that it did. There's other sinks for sulfate or sulfide. But he assumes that the missing sulfur in the sulfate showed up as FES. And then there are rate constants in the literature for the rate of degradation of TCE exposed to FES. You use the fastest rate. And they also compared the epsilon, the degradation factor on iron monosulfide, to the degradation factor that would have been carried out by biological reductive dechlorination. And he used the value for epsilon for the biology that had the lowest absolute value. Well, that's the worst in the literature. I really think, though, at this site we have production of vinyl chloride. There's a very good chance that the halococoides was doing some of that at least. And so the true value is probably not as conservative as the values that he consumed, but he had the lowest value for absolute value for epsilon for the biological process, the highest absolute value for the abiotic process, and he assumed that all the missing sulfur turned into the reactive component. He's got a paper in review on that. Hopefully it'll be accepted and it'll be out shortly. Until that happens, I invite you to send email to Pat McLaughlin.
Okay, so what would be the next step that you would recommend if the CSIA shows that degradation is not occurring in a site?
Well, it depends on your goals and how close you're getting to it. I have another EPA report on the statistical analysis of long-term monitoring data to see if the trends over a 5-year review cycle are appropriate for M&A. Eval M&A, EVAL M&A, be one of the keywords to search on. It's on the Ada Kerr Lab webpage. And this is basically ORD guidance that went through the EPA clearance process. And what it says is that you take all the wells and you look at the concentrations and you look at the trend lines and you see which well is the one that's likely to be the last one standing with concentrations above the action level. And that's the one you worry about, because that's going to be the one that limits how long it takes the entire site to clean up. So if you have a well that's trending the wrong direction, but it's way down there in the concentration list, that's not the one to worry about. You know, you can watch that little abiotic, or sorry, that little anomalous well for a while you're worrying about the high concentration well. The point of that is you make your decision about active treatment and you focus active treatment on the areas sampled by wells that are not going to meet your cleanup goal by the time that you're expected to meet the goal. So with that in mind, you take your decisions about trends and CSIA and next steps in that context. And it has to be in that context. If the performance of a particular well is going to keep you from meeting your goal, then you do something about it. If it's not the one that's limiting, then you wait and see what the future behavior will be. Read the question to me again so I can make sure I answered it.
Okay, what would be a recommended next step when CSIA shows that degradation is not occurring?
All right, and so if you have a situation where natural attenuation by anaerobic biological reductive processes has not kicked in yet, it might make sense to wait. I showed you one well where cis was just starting to degrade, If you look at the microcosm studies, the culture studies, very frequently the bugs work one compound at a time. There's an emphasis on TCE, and then an emphasis on cis, then an emphasis on vinyl chloride. There's actually some data from field scale that indicates that the microbial community will switch to different strains of D. halocolloides as one compound or another becomes exhausted. Apparently the different kinds of D. halocolloides specialize in more chlorinated or less chlorinated. So I wouldn't get excited about it initially if it's one of these wells that, like I said, the concentrations are low and it's not going to cause a problem, and we can wait for 5 years and see if something good happens. However, if we have waited that 5 years and it turns out this well now is going to limit the performance of the total system, then the next step is to start thinking about active treatment. And that's probably as much as I need to say about that. Next question.
All right, I think that's all the ones that we have this morning. If you have additional questions in the audience, you can email them to Dr. Wilson, or you can send them to me at info@microbe.com, and I'll get with him. We'll get those answers for you. Dr. Wilson, thank you so much for your presentation today. I'm really excited to see the paper that you and Pat have been working on. I think that will be very helpful, and I appreciate that you took time out of your busy schedule to do this webinar for us. And we hope that everyone in the audience will join us for future webinars in 2014. Thank you again.
You're very welcome.
Thanks, John. Bye-bye.
Bye-bye.